A quantum computer is an advanced computer that uses the principles of quantum mechanics to perform calculations at speeds unattainable by even the top supercomputers of the modern world. For most of our history, human technology consisted of our brains, fire, and sharp sticks. While fire and sharp sticks became power plants and nuclear weapons, the biggest upgrade has happened to our brains. Information in classical computing and classical information. In quantum computation and quantum information, a quantum bit or qubit plays a similar role. In this video, we will see what the qubit actually means and compare its properties to those of classical bits. To understand how a quantum computer works, imagine that you're playing a game of chess and want to predict all the possible moves your opponent might make. You can do this with a classical or regular computer. It will go through each move of your opponent one at a time until it runs through all possible moves. Since the 1960s, the power of our brain machines has kept growing exponentially, allowing computers to get smaller and more powerful at the same time. But this process is about to meet its physical limits. Computer parts are approaching the size of an atom. We're going to describe qubits as mathematical objects with certain specific properties. It is true that qubits, like bits, are realized as actual physical systems. The beauty of treating qubits as abstract entities allows scientists to construct a general theory of quantum computation and quantum information independent of any particular physical system. This process, as you can imagine, can be time-consuming. However, if you had a quantum computer, it would simulate all possible moves of your opponent at once in a fraction of the time the classical computer took. This is similar to what a quantum computer can do in the realm of analysis and computation. To understand why this is a problem, we have to clear up some basics. A computer is made up of very simple components, doing very simple things, representing data, the means of processing it, and control mechanisms. What is then a qubit? Just as a classical bit has a state, either 0 or 1, a qubit also has a state. Two possible states for a qubit are the states ket 0 and ket 1, which are similar to the states 0 and 1 of a classical bit. A quantum computer and a classical computer are similar in some ways. Both have circuits, chips, and logic gates to process information, and they are both operated by algorithms. Computer chips contain modules which contain logic gates, which contain transistors. A transistor is the simplest form of a data processor in computers. Basically a switch that can either block or open the way for information coming through, which are similar to the states 0 and 1 of a classical bit. This weird notation is called the Dirac notation and is a standard notation for representing a state in quantum mechanics. The difference between bits and qubits is that, unlike bits, qubits can be in a state other than ket 0 or ket 1. It is perfectly legal to have a linear combination of these two states. This phenomenon is called quantum superposition. The numbers alpha and beta are in general complex numbers. However, the primary difference lies in how they process information. Classical computers use binary bits, zeros and ones, representing the on or off state of a current. Quantum computers, on the other hand, use qubits, which can exist in both states simultaneously, a property known as superposition. This information is made up of bits, which can be set to either 0 or 1. Combinations of several bits are used to represent more complex information. Transistors are combined to create logic gates, which still do very simple stuff. For example, an AND gate sends an output of 1 if all of its inputs are 1, and an output of 0 otherwise. The special states ket 0 and ket 1 are known as computational basis states and form an orthonormal basis for this vector space. This unique ability of qubits opens up a world of possibilities, allowing quantum computers to process information in a fundamentally different way than binary bits and potentially revolutionize the future of technology. Combinations of logic gates finally form meaningful modules, say for adding two numbers. Once you can add, you can also multiply, and once you can multiply, you can basically do anything. Since all basic operations are literally simpler than first-grade math, You can imagine a computer as a group of 7-year-olds answering really basic math questions. A large enough bunch of them could compute anything from astrophysics to Zelda. However, with parts getting tinier and tinier, quantum physics are making things tricky. Let's now explore the fundamental difference between a bit and a qubit. It is always possible to examine a bit to determine if it is in state 0 or 1. For example, computers do this all the time when they retrieve the contents of their memory. Rather remarkably, it is not possible to examine a qubit to determine its quantum state. For learning the quantum state of a qubit, we need to learn the values of alpha and beta. However, quantum mechanics tell us that we can only acquire much more restricted information about the quantum state. Let's consider the concept of superposition using an everyday example. When you flip a coin, it can show either heads or tails. But when the coin is spinning in the air, what state would you say the coin is in? Is it heads or is it tails? While it's spinning in the air, it could be argued that it's both heads and tails, correct? As a group of 7-year-olds answering really basic math questions, a large enough bunch of them could compute anything from astrophysics to Zelda. However, with parts getting tinier and tinier, quantum physics are making things tricky. In a nutshell, a transistor is just an electric switch. Electricity is electrons moving from one place to another, so a switch is a passage that can block electrons from moving in one direction. Today, a typical scale for transistors is 14 nanometers, which is about 8 times less than the HIV virus's diameter and 500 times smaller than a red blood cell's. As transistors are shrinking to the size of only a few atoms, electrons may just transfer themselves to the other side of a blocked passage via a process called quantum tunneling. When we measure a qubit, we get either the result ket 0 with probability alpha squared or the result ket 1 with probability beta squared. So from a single measurement, we will not be able to learn the values of both alpha and beta. Thus, in general, a qubit state is a unit vector in a two-dimensional complex vector space, and measurement collapses it into one of the bases. Similarly, a qubit can exist in both the 0 and 1 states simultaneously. In a quantum computer, a system of multiple qubits can simultaneously possess multiple states, allowing the quantum computer to process many solutions simultaneously, something a classical computer simply cannot do. Scientists are trying to use these unusual quantum properties to their advantage by building quantum computers. Qubits' ability to be in superposition states runs counter to our common sense. A classical bit is like a coin, either heads or tails up. By contrast, qubit can exist in a continuum of states between ket 0 and ket 1 until it is observed. Let us emphasize again that when a qubit is measured, it only ever gives 0 or 1 as the measurement result probabilistically. This capability enables quantum computers to solve problems much faster than classical computers. The magic of quantum computers doesn't end with qubits and their multiple states. These multiple states of multiple qubits can be linked to each other, or in the language of quantum mechanics, they are entangled with each other. Entangled qubits work in a way that the operations of one qubit can influence other qubits, no matter how far apart they are, and can also influence the entire system. In normal computers, bits are the smallest units of information. Quantum computers use qubits, which can also be set to one of two values. A qubit can be any two-level quantum system, such as a spin in a magnetic field or a single photon. 0 and 1 are this system's possible states, like the photon's horizontal or vertical polarization. In the quantum world, the qubit doesn't have to be in just one of those. It can be in any proportions of both states at once. This is called superposition. For example, a qubit can be in the state which, when measured, gives the result 0 50% of the time, and the result 1 50% of the time. This state, which is in an equal superposition of ket 0 and ket 1, is quite an important quantum state and is sometimes denoted by ket plus. This allows for significantly higher computational power, something that classical computers cannot achieve. Entangled qubits function seamlessly due to a phenomenon called quantum entanglement. As soon as you test its value, say by sending the photon through a filter, it has to decide to be either vertically or horizontally polarized. So as long as it's unobserved, the qubit is in a superposition of probabilities for 0 and 1, and you can't predict which it will be. Although qubits seem strange, they are in fact real. Experiments extensively validate their existence and behavior, and they can be realized using a wide range of physical systems. In order to get a sense of how a qubit can be realized, let's see some of the ways it can occur, as the two different polarizations of a photon, as the alignment of a nuclear spin in a uniform magnetic field, as two states of an electron orbiting a single atom. Additionally, a quantum computer looks nothing like your regular computer or laptop. When you walk into a room housing a quantum computer, what you'll most likely notice first is large, complex-looking machinery, much like a chandelier, with golden, silver, and blue parts. Around it is a maze of wires, tubes, and other intricate components. The setup looks straight out of a sci-fi movie. Superposition is a game changer. 4 classical bits can be in one of 2 to the power of 4 different configurations at a time. That's 16 possible combinations, out of which you can use just one. 4 qubits in superposition, however, can be in all of those 16 combinations at once. This number grows exponentially with each extra qubit. 20 of them can already store 1,000,000 values in parallel. A really weird and unintuitive property qubits can have is entanglement, a close connection that makes each of the qubits react to a change in the other state instantaneously, no matter how far they are apart. This means that when measuring just one entangled qubit, you can directly deduce properties of its partners without having to look. In the atom model, the electron can exist in either the so-called ground or excited states, which we'll refer to as Ket 0 and Ket 1 respectively. By shining light on the atom with appropriate energy and for an appropriate length of time, it is possible to move the electron from the Ket 0 state to the Ket 1 state and vice versa. But more interestingly, by reducing the time we shine the light, an electron initially in the state of Ket 0 can be moved halfway between Ket 0 and Ket 1 into the Ket plus state. Quantum computers have been in existence in various forms for several years. In fact, some tech companies already possess operational quantum computers that serve as valuable resources for software development and programming languages. Qubit manipulation is a mind-bender as well. A normal logic gate gets a simple set of inputs and produces one definite output. A quantum gate manipulates an input of superpositions, rotates probabilities, and produces another superposition as its output. Historically, a great deal of attention has been given to the meaning or interpretation that might be attached to superposition states and to the inherently probabilistic nature of observations on quantum systems. However, for almost all practical purposes related to quantum information processing, it is not necessary to concern with such discussions. The most significant advancement in quantum computing in recent years occurred in October of 2019, when Google asserted that it had achieved quantum supremacy with its quantum computer. This entailed using their specialized Sycamore processor to perform a specific type of computation much faster and more efficiently than the most powerful classical supercomputer. So a quantum computer sets up some qubits, applies quantum gates to entangle them and manipulate probabilities, and finally measures the outcome, collapsing superpositions to an actual sequence of zeros and ones. What this means is that you get the entire lot of calculations that are possible with your setup all done at the same time. How much information is represented by a qubit? Paradoxically, we can do infinite binary expansion of values alpha and beta. So in principle, it could store infinite information. However, this conclusion turns out to be misleading because of the behavior of a qubit when observed. Recall that measurement of a qubit will give only either 0 or 1. Furthermore, measurement changes the state of a qubit, collapsing it from its superposition of ket 0 and ket 1 to the specific state consistent with the measurement result. For example, if the measurement of ket plus gives 0, then the state of the qubit after measurement will be ket 0. This demonstration of quantum supremacy validated the concept that quantum computers can indeed surpass classical computers in specific tasks by leaps and bounds, and can execute operations that classical computers cannot. Ultimately, you can only measure one of the results, and it will only probably be the one you want, so you may have to double-check and try again. But by cleverly exploiting superposition and entanglement, this can be exponentially more efficient than would ever be possible on a normal computer. Why does this type of collapse occur? Nobody knows. Until now, we simply accept it as a law of nature and include it as one of the fundamental postulates of quantum mechanics. What is relevant for our purposes is that from a single measurement, one obtains only a single bit of information about the state of the qubit, thus resolving the apparent paradox. This progress also prompted other companies, such as Microsoft, IBM, and several startups, to intensify their quantum research in pursuit of even greater results. So while quantum computers will probably not replace our home computers, in some areas they are vastly superior. One of them is database searching. To find something in a database, a normal computer may have to test every single one of its entries. Quantum algorithms need only the square root of that time, which for large databases is a huge difference. The most famous use of quantum computers is ruining IT security. Once the full potential of quantum computers is realized, it will herald a world of truly unimaginable possibilities. Quantum computers have immense computational capabilities that will greatly enhance artificial intelligence. Right now, your browsing, email, and banking data is being kept secure by an encryption system in which you give everyone a public key to encode messages only you can decode. The problem is that this public key can actually be used to calculate your secret private key. Luckily, doing the necessary math on any normal computer would literally take years of trial and error. But a quantum computer with exponential speedup could do it in a breeze. Nevertheless, there is something conceptually important going on here. When nature performs an operation on a closed quantum system of qubits without performing any measurement, she does keep track of all the infinite parameters of alpha and beta, even though that information is hidden from us. Nature conceals a great deal of hidden information, and even more interestingly, the potential amount of this extra information grows exponentially with the number of qubits. Understanding this hidden quantum information lies at the heart of what makes quantum mechanics a powerful tool for information processing and the future of computation. Quantum cloud computing services have the potential to revolutionize machine learning by processing extensive amounts of data and complex calculations at unprecedented speeds. Another really exciting new use is simulations. Simulations of the quantum world are very intense on resources, and even for bigger structures such as molecules, they often lack accuracy. So why not simulate quantum physics with actual quantum physics? Quantum simulations could provide new insights on proteins that might revolutionize medicine. In cybersecurity, quantum computers could uphold data encryption during active use, providing robust protection. They are also poised to revolutionize medical and drug research, weather forecasting, and automobile battery technology. Right now, we don't know if quantum computers will be just a very specialized tool or a big revolution for humanity. We have no idea where the limits of technology are, and there's only one way to find out. While it will take many years before quantum computers become mainstream and see large-scale commercial use, it doesn't seem like an exaggeration to say that quantum computers will eventually be powerful enough to not only solve complex problems, but also help you find your missing socks. Predict the outcome of your next dinner date, and maybe even explain why you walked into the kitchen only to forget why you were there in the first place.